So welcome everybody. We are on the YFTT. Every Friday we do this talk from engineers to engineers, and today we have a topic that looks very simple, counting rows in a table, but on large table it can be problematic, and then there are different solutions. And to talk about it and to demo about it, we have Naitik. Naitik, you can introduce yourself, and the floor is yours.
Sure. Thank you, Frank. Hello, everyone. I'm Naitik Shah, and I'm a part of the customer success and services field team here at Yugabyte. We engage with our users at various stages of deployment, and our goal is to help them get the best value out of Yugabyte. So today's YFTT topic is counting rows of large tables. And I'm going to cover a few approaches, right? And those are all based off of, or most of them are based off of Frank's blog on the same topic. So I'll be sharing my screen here, and is my screen visible? Just
Yeah,
verifying.
I can see it. Yeah.
Okay. So let's go ahead and get started. All right, so here is the quick agenda, right? So we'll go through the problem of counting rows. And that would cover when or why we would count rows, and then what are the issues, what are some of the common issues with those. And then, of course, some of the approaches, including getting an approximate count for a hash sharded table, parallel scan based on the hash ID. We'll also cover counting of large tables in YCQL, right? So the first two approaches are in SQL. We'll cover one of them for CQL, and then also go over an increment counter on row inserts or updates, and that's applicable to both YCQL and SQL. And then towards the end, we'll see if we have any questions. All right. So when and why do we need to count rows, right? So there are different scenarios. Of course, you're running a reporting or analysis on your data set. You want to get estimates of how large your table is. For example, if you have a user data, and you may want to get estimates of how many users are actually using your platform. In that case, you may have to run a count, right, on the number of users or your app data. Validation, data validation would be a scenario when you're moving data from one system to another, and you want to verify and validate the data. Query optimization is and another thing, right? The select count statement in the SQL world is commonly used to retrieve, the number of rows for a given condition. You may want to see if the data is distributed across how many rows does a query fetch, right? Things like that, and run explain plans or explain analyze, right, on some of the queries. So that's where query optimization may also include running counts. Um, so why is this a problem, or why this could be a problem, right? So data is distributed across multiple nodes within Yugabyte, and into multiple shards, right? And we call them, or we refer to them as tablets. So if you think about it, when you're trying to count the data across different nodes, you could easily get into a scatter gather problem, right? Where a single node is receiving the query from the client. You're trying to fetch the data from all the nodes. And then again, this single node is going to try and aggregate everything and then send it back to the client, right? So it's not efficient, right, from that perspective. So resource intensive, it could really get um, uh, you could use a lot of CPU, you could use a lot of you end up using a lot of cache or memory, right, when you're trying to scan through the entire table or all the rows. And then, of course, long execution times. Count star query is considered like an anti-pattern, and it generally involves a full table scan. right? In almost any databases, and the table sizes in some cases can go really large, with millions or sometimes even billions of records. So that's where uh, we need to be efficient, right, in terms of how do we solve this problem. So and we'll cover those. And then of course query times out, right? In case of large tables, you may just see a pound star query timeout. All right, so let's look at the first approach here, and that is getting an approximate count of a hash table, or a hash sharded table. Right, so we have a couple of sharding mechanisms within Yugabyte. One is hash, and that's the default, and the other is range. Here in this approach, we are covering just the hash sharding, or a table which is hash sharded, right? So just a quick overview of how Yugabyte distributes the data across different tablets, right? So on the left here, you see a table, and we have the primary keys. So the hash value of the primary key is taken into consideration, and based off of that, this row or the data set, right, is placed onto a particular tablet, right? In this case, tablet number 1, and the same happens for primary key with number 4. So you could see the color coding, and you would get an idea of how this is being distributed across multiple shards or tablets. And all of these each of these tablets is of course based off of a hash range, right? Um, and our hash range, or it goes up to 64K, right? So this would be, let's say the first tablet, for example, goes from 0 to 512, and then the second from 512 to 1024, and so on and so forth, until we get up to 64K, right? So that many tablets is that we can get to. Now, YB hash code is a built-in function that we are going to cover here, for getting the approximate count of a hash sharded table, right? So if you look at this query here, right? So you look at this table schema. It's the K is a primary key, and when you're trying to select star from this table, where you're having a YB hash code and you're trying to scan through a particular tablet, right, or a particular range within the tablet range that we just covered. So in this case, you're looking for the hash ranges greater than equal to 512 and less than 1024. Right? So in this case, if you look at, assumption here is the hash boundaries are on here, 512, 1024, 1536, etc., and so on. So in this case, you would be covering all the data that is residing on tablet number 2. Right? So that's where all of this data would be residing. Now, YB hash code function in general, right? It has a lot of other uses as well. We use this for verifying the tablet health, overall data distribution, just to make sure whether the data is distributed across evenly, to get the table size estimates as well. And of course, the other use is to get an approximate count as well, right? And we'll come to this in terms of being able to run parallel queries. So what this is telling here is you could run a query. So for example, like this one, right? And then you could have multiple such queries trying to scan data just from a single tablet, right? So in this case, you could have 4 different queries with different hash code ranges, and get the total of the, sorry about the screen, yeah, and then
No problem.
get the total value, right, or the total count of all these queries. So that's what I mean here by distributed parallel queries, and we'll cover that in the demo. So um, after each session or after each approach, we'll have a demo there. So in this one, you will demonstrate, we'll count 140 million records using the YB hash code function. We'll get an approximate count within 25 milliseconds, right? Yes, 25 milliseconds versus 15 seconds if you run like just a regular count star. So it's time
So
for.
while you said the demo, maybe I can mention this YB hashcode function can take any data type, and I think can take even multiple columns, because you can hash on multiple columns and then you pass all the primary key hash part to this function.
Yep, that's perfect. So so here I have a 3-node cluster of Yugabyte, and then just want to clear the screen this way. So I'll just turn timing on first of all. That way we'll get the count, and then I'll just do. So this is the table that we are going to look at, demo 1, which has ID as the primary key. And we can also do a quick. Yeah, so we have data, you have UUID in the ID column, that's our primary key, and then some values here. So what we are going to do is we're just going to try and run a simple select count star from demo 1. And we'll see how long this takes. So yeah, so this is taking approximately 3 seconds in this case, and we can run. So the query that I'm going to run here, right? It's we're going to run it with explain analyze, but I'll just explain the query here. So we are running a count star from demo 1 with YB hash code of the primary key column here, that is ID. And what we are doing here is these are the total number of hash ranges, right, that we could have. So that's 65536, which is 64K. And we are dividing this by 1,000, which means this would be 0.1% of all the rows that we have in the table. And while we are just counting rows, or 0.1% of the rows here in our end result, right, for the projection itself, we are multiplying it again by 1,000, right, just to make sure that we're close to what our actual number should be. Right, so that's what this does. And if you look at this one, it says, yeah, of course, the total time was 26.
Much faster, yeah.
Yeah, that's pretty fast. And then if you look at the query plan itself, right? So we were just doing an index scan in this case. It's not like a full table scan, and it's of course getting. Let me just see.
So it reads, maybe we can mention that in Yugabyte, we store the table in the primary key, and then it looks at a range of it.
Yes. Yes.
Smaller than the full range.
Yeah. So, yeah, so exactly. And you can see this value is very, very close to what we got, right? 140 million. So it's this time, and again, this is an approximate value that we get. Now we can extend, of course, this use case to sample a batch of rows by selecting, over a random, fixed number of intervals, like we mentioned earlier, right, over the hash partition space. For example, you can select over a random 5 and 2, and then this would be like 1 by 128th of the actual hash partition space that we have. And we could run some queries like this. For example, so it would be, so this, in this case, we are trying to get all the records, or the count for the records for the hash value between 0 and 512. And we can run multiple such queries. So in this case, I'm just changing the range here from 512 to 1024. And you could see, I mean, in our case, the data is pretty much evenly distributed, right, based on this number. And you can see each query takes just a few milliseconds, right? So it's not, and then you can basically sum it all up towards the end, and this will give you the total count at the time of running this query. Of course, it's not gonna consider the data if the application is still writing to the table, and if it's continuing to write, of course, you won't see those records in the counts. But yeah, that's where you can get the actual total count of all the records. Anything you want to add here, Franck?
No, that's fine. And then you can run that in parallel, because you know that it reads different ranges physically on different range in the LSM tree, or even in different tablets, and so different nodes.
Yes. Yep. That's correct. So we'll go back to our. So yeah, our next approach here is parallel scan based on the hash ID. So if you remember, like we mentioned about the scatter gather problem, right? So this would be a divide and conquer strategy, right? And that's going to be a solution to that. The major benefits of these are this is built in within Yugabyte. So there is performance enhancement already within the database itself when we run such queries, and we'll go through that as well. So in order to demonstrate this one, we are gonna have two scenarios. One is without parallelism, and one is with parallelism. What this means is, in our example, I've created one table. So let me just go through the demo, that way it's easier, right?
And if people have questions on the chat on LinkedIn or YouTube, do not hesitate.
Yep. So let me just connect to. Yeah, so I just have two screens here side by side to make sure that we are looking at two different tables. So on our left, we'll look at demo2 table, and on our right, we are going to look at the demo table. So if you look at the actual schema, right, it's the same. Both have the same exact primary key, and it's a single column table. It's a very straightforward table. Now, the only difference between both of these is the number of tablets that we have assigned. So this demo2 table, it has just single tablet, and the count 3 here just tells us how many T servers we have. So we have 3 nodes running T servers. And on the right, we have the table demo, and that has been created with 12 tablets. So that's the only difference between both of these tables, and we can see the difference, right, in terms of how long it takes, right, to run the counts on each of them. So I'm going to run explain analyze select count ID from demo2, and then same thing for the demo table here, and we'll go through this. So As you can see here, the execution time on our left for a table with a single tablet, it took about 3 seconds or a little over 3 seconds, versus for a table on the right which has 12 tablets, it took almost half the time, right? And if you look at also the number of rows here, um, so in this case, it's just going through one row, versus here we see that it does go through 12 rows at a time, right? So in this example, we are basically saying, there are, of course, parallel connections, right, to multiple tablets within Yugabyte, and that's how we get this optimization, right, in terms of being able to execute it faster, right?
And each tablet does a partial aggregate. That's what we see, partial aggregate true. And this is why it returns one row, it's the partial aggregate. The other, so the other already runs in parallel, even without, with a simple count, it is already parallelized internally.
Correct. Yep. Yeah. And this is just an example to show like how parallelism is there. I mean, by default anyway, we do not have tables created with a single tablet, but yeah. And all right, so I think that is it on this one. Any questions so far from?
I don't see any question on LinkedIn. I hope I refresh to be sure. I hope I didn't miss them.
All right, sounds good. So we'll go through our next approach here, and that is for being able to count on YSQL, right? So when you have a large table in YSQL, how would you do that, right? So YCRC is a tool. So we call it as YSQL row count. That's the abbreviation. And this allows basically counting rows in a large, YSQL table, and this uses the same approach of what we just went through, right? Execution of parallel queries across smaller partitions, and then sum these all up, right? So in this case, we'll run YCRC for about 10 million records, and it takes 13 seconds. Right? So.
So just to mention, we have multiple APIs. The most common is the SQL API, where we use Postgres, and that's why SQL. But we have also a YSQL API for application that can move, for example, from Cassandra. They can use exactly the same syntax. It's still the same storage that is fully ACID, but we have this Cassandra-like API.
Yeah.
And there is also a different, the advantage of the Cassandra driver is that the drivers connect directly to the different nodes, where in SQL, it has to connect to one node that manages the session because the transaction can be more complex. So here, I think you will have some parallelism directly from the driver.
Yeah, that's correct. So in this case, I just have again a sample table. It's where column 1, 2, and 3 are the partition keys, and column 4 and 5 are clustering columns in this case. And I'll just do select star from table 1 just to show the data set. So yeah, we do have some random data, test data as well. Now we're going to run YCRC on this one. So YCRC is a tool, and we have shared the GitHub link. That's something. So this is the command, right? So it's a pretty straightforward. It has specific options that we need to provide. That one is, of course, the key space name, the host that you're connecting to, credentials, and then the table, right? So we'll just run this, and these are the default. I mean, there are additional options for being able to tune the scale, the parallelism, and even the timeout. And I can show you how that looks like as well. And so by default, when we run, it runs 16 parallel tasks, and it took close to about 11.6 or 12 seconds. And we can see that the total row count for this table is 10 million. Now, we can also run this with, let's say, I mean, this is just to demonstrate um, how it would work, let's say, with a single thread, right? For example, if you look at these options now, so this is -s is for scale, this is for parallelism, and this is for the timeout. So in this case, it's just running with a single parallel task. So of course, it's going to take longer and than what we saw here, right? So yeah, so it took about 24 seconds in this case. All right, so this gets us to our final. I think there's another tool as well which we are not covering here. We have seen a lot of users use the DS bulk, which is again a Yugabyte forked version of the DS bulk tool that is available, and you also have count functionality there. And one of our, I think, blog posts or the documentation covers that, so could take a look there as well. Of course, this is something we already covered. Now
we have a question from Anjuman. How do I know the shard ranges if automatic tablet splitting is on, or always we have to count based on the highest range value it can have? So you have used the YB table properties to show the number of tablets in YSQL.
yes,
That's right. And
yes.
I think we can also see it in the console. But basically, we cannot really see it with the range value because the range will always fall between 0 and 65,535. But yeah, exactly. You have the first column of the YB table properties. You can also select from YB table properties. The first column is the number of tablets. So if automatic tablet splitting is on, then you will see this number increase.
Yeah. Perfect. I can run a select if you want. I don't know how much it's going to give me. Okay.
Yeah, and it takes the OID as a parameter, the name.
Yes, I think
the
this
name of the table that is casted to wake class to get the OID, as you did before.
this might require, yeah. So you're saying demo? No, no.
Oh, you can copy paste from above YB table properties, and in parentheses. Yeah, you got it.
I think we want. Will this display the number of? Yeah. Okay, there we go. So yeah, and I think so. Basically, it's an approximation, right? When we choose the hash ranges, it's an approximate value, and it can't be fully accurate. Saying this is at least when we run these count start queries. All right. So the last approach here is increment counter, right, on the row inserts or deletes. Now, this approach, of course, it's a lot of folks might be familiar with this already, right? So in this case, you have two tables. One is, of course, the data table, and then the other is the counts table. So you're basically inserting data into the data table and then updating or incrementing the count by 1 every time you're inserting a value in the data table. Now, of course, depending on the use case requirements and the SLAs, you could choose this approach if it fits your needs. But it's the fastest approach overall, right? Just with a slight penalty of writing a transaction, right? Which means in this case, every time you write a record, you'll have to update or increment the counter, right, for the counter table as well. So that's the only penalty that you would hit, but it's a small one, right? If your app is able to do that, then this is a good approach. So we'll just go through this demo quickly as well. Quick check on the time. Frank, are we good?
Yeah, we have a few more minutes. Yeah, we
Okay.
can.
All right. So for this one as well, I can use the current sessions that we have here. So I've already created the tables. Clear the screen.
And while you do that, maybe I can mention we have seen on the slide that you are using a modulo 10 because, of course, this is scalable only if you have multiple counters. You don't want to ingest a lot of data from multiple sessions that will all update one single counter. So you probably want multiple buckets to distribute that.
Yes, that is correct. Yep. So I have two tables right now, and all I'm going to do is, in this case, run some inserts into the count table just to make sure that, like Frank mentioned, we're taking a mod of 10 here.
Yeah.
That way, our count table doesn't get as large. So just quickly verify. Oops. So yeah, we have 10 rows, and then you see the count right now is set to 0. Now we'll start inserting data and or values into our data table. And here I'm just running a for loop for inserting like 1,000 rows. And you look at it, it inserts and then also updates the counts with by incrementing a counter value, right? And this is again mod 10. So it'll be one of the 10 buckets or 10 counters that we have. And run the same thing here. So now each of these is 100. And in this case, I mean, it was even number, but yeah, we can do a sum here, right, real quick. If you do a select sum of count on counts, and you would get the total number of records in your table, right? So that's a pretty straightforward approach for. So this is for YSQL. For YCQL, we already have support for like a counter data type, so you can directly use it. You may not need even these two separate tables, right? In a single table, you could have a column that is with the counter data type, and which you can increment or decrement based on your needs. So yeah, with this, I think I want to definitely mention Frank's blog here, so it has a lot of approaches. You definitely want to review this, and it also includes, how would you run counts on, a range sharded table, right? So especially for the range sharded table, you would have to use an approach, something like a partial index with a materialized view. Frank also has a function for YB approximate count, basically for the hash in the example that we did earlier, that you have to find the primary key. To Frank's point, you could have multiple columns for some tables versus a single primary key for certain tables. So if you don't want to do that manually, you could of course write a function to get into the catalog table, fetch the primary keys, and then run the counts. So that, and then I think you've also covered hyperlog log, right? HLL in one of your blogs. So that in itself is a YFTT session of its own. It's pretty detailed and can't cover, of course, in the time that we had today. So that's that, and then we also have the support knowledge base, which covers both approaches, right? For counting, for running count in YCQL as well as YSQL. So both of the APIs are covered here as well. So you may want to check those out. Then yeah,
Okay, I'm checking if there are any questions.
yep,
I don't see any question. So yeah, that's good. We are on time. That's really interesting. So basically, those are trade-off between approximate count that is fast, longer count that is exact, more on the updates rather than on the selects. Many trade-offs just to avoid to read all rows and count them when it is needed.
yep. That's definitely
Okay, if we have no questions, then that's perfect. People can ask questions later on the community Slack on GitHub. Do not hesitate, and thank you very much.